going to the left side, yes, let's record the meeting, of course. You see that the 35 and 45, you have a slightly decreased correlation, but it's still quite linearly correlated. But 25 and 15, you see there's no variance in this prior ensemble, so there's no covariance actually. So if you have some information in this spatial point, it probably won't change anything over here. What's interesting to look at the other side of the hill. So this 55 versus 45 is actually anti-correlated, which means if you have higher value in the red here, you have lower value over the other side. So if but we can still change the value on the other side because we know this is negatively correlated. We can fix the value. So yes, this is a result after updating. Actually, only using one spatial point in a domain, we can just almost fix everywhere in this case. Quite amazing. So, however, if we introduce nonlinearity, this becomes not the case anymore. If we look at an ensemble with a larger spatial disperse, now the scatter plot does not look linear anymore. Some problematic points like here, you actually have a curvature in this distribution, which is non-Gaussian. So if you run the ensemble common filter, what it will do is trying to fit a line through this curve, which may look something like this, and trying to push these points along this line, shrink it towards the red line here. And what the resulting analysis update will be something off, not on this curvature anymore. So it will actually be centered here. So now the X55 value will, of course, have large errors. And a spatial point of view, you find that the updated function for each individual member will no longer be the nice Gaussian shape, especially for the blue member. You see there's like a second mode appearing. This is the behavior when you try to stick a linear update, like an ENKF solution to this kind of a nonlinear problem. It will always give you some result, and from the ensemble mean point of view, it may be still looking quite nice, but actually, if you investigate the distribution, it becomes not so good. What I propose to do in the multiscale framework is that we can look at the large scale component of these fields first. If you do a large scale bandpass filter to the Gaussian function, a Gaussian function's large scale component is another Gaussian function with a slightly broader spread. So in this case, you see the curvature gets reduced. This is a prior field of the original distribution, original field. Only we're filtering out we're basically smoothing the spatial field to get the large scale component. This, I believe, from the naked eye, you can believe that it's easier to update by the ensemble common filter because things are more Gaussian. And indeed, if we run the ENKF, we see there less of a nonlinearity going on the large scale. What's the magic is you can use this kind of information because from the prior to the posterior at the large scale, you're basically changing the location of this function. We can explain what happened after filter update is that we have a difference or analysis increment, and this analysis increment can actually be explained by displacement vectors. So we can compute, for example, this red member, how much towards the center it should move based on the before and after change in the filter. So this displacement vector that I compute, I can apply it to the full resolution field. Now you see that this kind of motion has a very nice feature comparing to the original ENKF update. You see that we're gathering their location instead of just changing the spatial value. What we can do again for the small scale is we precondition the whole field with the large scale displacement error. Then using this new ensemble, which is more centered, we can take out the small scale component looking like this. And now looking like this, we can run the Kalman filter again to constrain the small scale, which looks like this after the ENKF at the small scale. Now you sum these two scales together, you get the final analysis. Comparing the traditional or original ENKF method with the multi-scale alignment method, you in this simple case, you find that it's giving better analysis mean and analysis members. In real life, things will be more challenging, of course. The only uncertainty in the previous example I show is the location of the center of the Gaussian function. But in reality, you may have amplitude and the size differences of these functions. So here I'm showing an ensemble with other error sources. Now, if you look at the scatter plots, it's no longer a curvature, but just a cloud. This is more likely what we see in our real application. When you try to update something, then the correlation decreases over the distance, and you can no longer tell what happens over here by this observation. So of course, this will be more challenging for the method, but you can still apply the Gaussian ENKF at the large and also the multi-scale alignment too, and compare their differences. Okay, so I think here I probably can stop and see if I have any questions in the chat. Yes, I have one question. Yes, does modes that you or scales you are, this is a sentence I'm trying to understand, you're trying to best estimate with ENKF are, for example, the one terms of the Fourier series. Yes, you can choose different schemes to do scale decomposition. You can either use a very empirical one, like just smoothing, run a running average smoothing of the field to get the large scale component, or you can do a Fourier analysis. You can run the forward Fourier to get the spectrum, and then set a response function saying, keeping only the large scale wave numbers that you define for the large scale, and then do an inverse Fourier transform and back to the state space. Yes.
Also have a question.
Questions from the hack.
Maybe, yeah.
So non-physics is the question. Can anyone clarify to me what is meant by I use a Gaussian state for, yeah, okay. So that's what Patrick also asked. So I use a Gaussian function shape for my state variable. So to be kind of general, that's not a distribution, that's a state variable. And are you using or assimilating several times the same data with this multiscale? And if yes, isn't it an issue? So in the example, I'm showing only assimilating one observation at one time. Yes, in real application, you will need to do cycling and you assimilate several observations so that kind of accumulates the effect of what I just showed. So you have multiple observations, maybe in the vicinity of this area. And if you assimilate the one, what happens is what I showed. And if you assimilate more and more, this observation impact gets accumulated. Now, over time, which means I will show a little bit later in the tutorial, Python tutorial, that you need to have enough ensemble spread to correctly characterize the uncertainty for the next cycle. If you collapse the ensemble spread too much in this cycle, and the next cycle, the model dynamics doesn't increase it, you have a problem. So we need to inflate the ensemble spread probably. Yes, and always, if you assume the wrong distribution type in your problem, you always see some kind of a symptom. So if your problem is truly nonlinear and you assume a linear Gaussian distribution and you run the ENKF on this, what you will find that problems of outliers and bimodal distribution, you're missing the other mode, and the dynamics doesn't want to go back to the correct trajectory. This kind of problem will occur in nonlinear problems. I have another question. Low pass filtering or spatial running average thinning are linear transformations. How to reconcile the fact that the common filter or ensemble common filter already works optimally with linearity with the observed improved performance of the MSA scheme? Yes, that's a problem from Patrick. I think you're right that when the problem is optimal for linear ENKF common filter, we don't need to worry about using this additional multi-scale scheme because it cannot beat it. If you can go back to the very early case that I have not a very big ensemble location spread, it's actually ENKF give you the optimal solution, so you should just use the ENKF. But in reality, I'm saying that when you don't have enough observation to constrain it fast, more frequently, or you don't have very good observation to provide the information at some scale, and then you need some sort of a non-linear update, very fast non-linear update on this problem. So yes, I agree with you that when everything is linear, so don't bother, just use a common filter.
You don't have to agree. I mean, it was more of a question because I certainly see that the scheme makes intuitive sense, but I'm left with the question of how something linear will improve a scheme that is already good with linearity. And yeah.
Well, this spatial filtering is linear, but the problem with the position error, for example, is not linear. If you have a linear error in the coordinate of the feature, for example, the Gaussian, so what you have is error in their location. The location error distribution is actually normal. But if you look at spatial value, so if you take a spatial point and plot the distribution of this height, that's not linear. So for example, if you look at the hurricane, if the hurricane location is off, their location can be off by a little bit, so normal distribution. But if you look at cloud temperature in these fields, what you plot is a skewed distribution mostly, yeah.
Yeah, that's true, but the method relies on spectral decomposition, which is a linear transformation.
Yes, the alignment itself I haven't shown yet is not a linear solution, but yes, the multi-scale components are linear combinations of the original field. Yeah, but what I adding some nonlinearity by solving for the displacement vectors, and these vectors are nonlinear solutions. A question from Kimbok Lee. Sorry, but I am confused the meaning of filtering out the large scale component for MSA method in page 10. Yes, page 10. Did I lose my screen? Share. Page 10. I cannot see my page number. I'm crowded by the chat. Yes. Page 10. Where's page 10? So filtering out means run the spatial averaging. So if you look at the original field, you have this function. So this black curve is original state variable, which is at some resolution. Now filtering out the small scale means we run like smoothing operator on this field to get out the small scale component. And what you have left is a broader, so it's a coarser resolution version of the original state. I hope that answers your question. If no more, oh, I still see more questions coming, but I think we need to move on to the tutorial. Otherwise, we don't have a chance to see it. Don't save. Okay, I need to share other screen here. Okay, so if you go to the link I provided in the chat and click on the opening collab button, you'll have a realization of this notebook here. So in this tutorial, I use a two-dimensional vortex, slightly more complex. Now it's 2D than 1D. So what we do here, maybe you can collapse the sum preparation part and run everything. So it basically defines all the functions. Okay, let's do. So the first thing I want to do is let's get to know more the spectral space. What do I mean by that? So take a look at different spatial fields and their corresponding two-dimensional spectra, which is a spatial field A here defined by X and Y direction. If you compute the 2D spectra, I have a hat defined on the 2D wave number, and 2D wave number is the square root of this kx squared plus ky squared. Do I need to increase the font size? So maybe just increase it a little bit. Okay. So the power spectrum look like this for a power law of 1, which is white noise. If you think about one dimension, and the white noise has equal energy distribution on all the wave numbers, but for 2 dimension, you have a combination of this X and Y direction. So for higher wave number, you linearly growing modes. So this follows a powers. I cannot see my own page, that's the problem. So here you have a +1 slope in the 2D power spectrum for white noise. What happens if you thin the white noise? This is a thing with a interval of 4 grid points. What happens in the spectrum is this thinned field has a slightly shorter spectrum. You cannot resolve higher wave number than this number. And also the error variance, spectral error variance is elevated by a number of 16 times. So this is because you have less power also in the large scale. So I usually think about a white noise spectrum as you have a delta function situated on each grid point individually. And white noise means they are all independent. So a delta function will project to all the scales. So if you think about the large scale, you have this number of grid points, this number of delta functions all contributing to the large scale. And we know in statistics that the number of sample actually change the spread, change the variance. So if you have more things to constrain something and the spread should decrease. So for the large scale, you have error variance in a certain level. But now if you thin it, you reduce the number of delta functions to contribute into that large scale. So you have a boost in error, if that makes sense. But here I actually give rise to a problem called representation error, because for some application we have very dense observation. It kind of resolves a finer scale than what our models can resolve. So if you imagine this is what we observe in space, and what our model can do is probably not resolve these high peaks. We have a lower resolution than necessary to do that. So our model probably see the observation in this fashion, which is kind of wrong, because now if you take one spatial point, and you say this is the representation of this whole neighborhood of the 4x4, then it's erroneous, because now you're saying the adjacent points are also high value, which is not the case in observation. So what we need to do is actually to smooth the field, which we also call super observation. So this is a nice approach, because when we smooth the A field, now if you only have a reduced grid, it still follows the original error spectrum, which will be correct when we assimilate this information. On the other hand, if we change the white noise to a red noise, things will be slightly different. The red noise will also be called the spatially correlated error. So this error will no longer be independent from each other. They are all growing high value in the vicinity together. And in this case, both thinned observation and the smooth observation will give the same error spectrum. You don't need to worry about representation error in this case. So now let's play with the model. If you move this out of the way. What we can do is here we can define our parameters, the model parameters, how large the model is, and the spatial density of the observations, time, frequency of the observation, and the measurement error power law of the observation, how long you want to run the model, and the filtering is whether or not you want to run the filter, and ensemble size. On the scales here, I define a number of different scales using the pyramid level method, which means you have an original model resolution of 32 by 32. This is the first level. So here I put 1. So this means the original method, so the full single scale. Well, we have here, if I have 3 and 1, this means I include one larger scale with resolution reduced by 4 times. And the smaller scale component. Again, these are 2 scale systems, so I can use. So I will run this first. So this will give us a no DA case, how the error look like. And of course, it takes a while to run. And let's visualize the result. So what you see here is the truth of this vortex that I created as my model state variable. So this is a U component wind of this vortex. I highlighted one contour here in black. And on the second plot, this is ensemble spaghetti plot, which is the black is the truth, but the colored ones are from the members. You see that they are starting to diverge from each other as time goes. So in the error power spectrum, you see the signal of this vortex is at this level. So you have more energy in the large scale than the small scale. If we plot the error, which is the ensemble mean minus the truth, and then you compute its spectrum, the error spectrum is going up and up. First, the small scale error matches the signal itself. It's the biggest error you can get in the system, and that we call error saturation. And for some system, you have error saturate first at small scale, and then it grows up, it cascades up to the larger scale, and the large scale eventually will saturate too. But in this case, we have data assimilation to push the error back. The ensemble spread are shown in the dotted line here, so it's kind of matching the ensemble error, which is supposed to be. It's defined by computing the ensemble perturbation, which is ensemble member minus ensemble mean, and that difference is computed to the power spectrum, and you sum all the power spectrum of the member and divided by n minus 1 to get the variance. So spectral variance is defined this way. But if you compute domain average sense the root mean square error and the ensemble spread, you see that it also grows. It's actually growing in time. So this is a no DA case. What we can try to do next is run the actual ensemble common filter. We can set the run filter to true, and yeah. So for now we just do this filtering, and we probably will only have time to demo this part because I see I only have 10 minutes left. Oh wait, not 10 minutes left. 40 minutes left. So what you see is I run the forecast for t equals 1, and then the next time step you have running on some common filter and running the forecast, running the filter. If you visualize the result here, it's showing a sawtooth graph. So the error grow in the forecast step and the decrease in the analysis step. And now in this case, we have observation every cycle. So it kind of keeps decreasing. We expect it. But also if you find that the ENKF give you kind of funky shape vortex, that is also a problem with localization, which I will show later. Another thing I want to quickly mention here is observation information content. So what determines how our filter performance should ultimately become is how much available information you have at hand. So you can have a very dense observation, but only very available every 12 hours. Or you can also have a coarse observation resolution, but available every hour. It should sort of give you comparable information. Ultimately, you have very high resolution and high frequency of this, and the problem becomes very linear. Let's demonstrate how that will be the case. This will be reducing the observation density to 1 breakpoints, and also maybe reducing the variance. Let's not do that. Yes. Yes, probably that. Yeah, since we reduced observation resolution, this will take significantly longer time to run. We can maybe take the time to answer some questions. I have one question. Can we apply the MSA on other filters, like particle filter, for example? Of course. The multiscale loop is built on the state space, and when you try to update each scale component, you can choose whatever kind of filter, whatever flavor, whatever type to update this component. Yes, of course, I can apply a particle filter for the update of the large scale component. It will do an even better job to address the nonlinear relationship between full resolution observation versus this large scale component state. Yes, it's a very good idea. Anything in the chat? No? So in the following example, I probably will reduce the number of time steps just to save time because it will just keep running. So there's a compromise I made in designing this tutorial. You cannot afford to run a full nonlinear multiscale system in this tutorial because it will just be a bigger model that you cannot afford to run. At the same time, if you use only the vortex model I show here, it's a very small 32 by 32 model. It actually doesn't contain the necessary nonlinearity in the dynamics because you cannot yeah, the error doesn't grow fast enough at the small scale in my current formulation. I'm still exploring a way to maybe in a similar fashion to the Lorentz system that I can incorporate some very random stuff in this simple model, so I can demonstrate behavior. Basically, in the tutorial, all the demonstration, I still have difficulty showcasing multiscale method, which is superior than the original YingCAP. Currently, the YingCAP is give you the optimal solution, which is kind of against the purpose of this tutorial, unfortunately. Yeah, but we can still see the mechanism of how the algorithm work. Yeah. So with more frequent updating, the funky shape of this vortex became more alleviated. You see that I am having lower error overall, which is quite satisfying to look at itself. Yeah, and this already gives you all the mechanism you can play with. After the tutorial, if you are interested, you can just play in this sandbox by changing all kinds of things and try to break it. I already break it many times in the past week when I'm developing the method. One thing we can visualize in the next cell is we can look at the error in the state in spectral space. So in here, the state space. This is observation error looking like a random noise, a white noise. And the prior error looks like the vortex, because if you smooth out, if you average the average all the members, you have ensemble mean, and because they are slightly different, the vortex will be weaker in the prior mean. And if you take that and subtract the truth, you'll have some amplitude adjustment as well as the background flow too. So there are some difference, but this is not looking like a white noise. This is a very correlated error. So we are kind of blessed in our DA practice that mostly our prior error doesn't look like a white noise. Let's think about this problem. If our prior error looks like something like the observation error here, what does that imply? That implies we need to have individual observation on each spatial point to constrain the solution, because now all the errors are uncorrelated. We cannot use one spatial point to infer something in the other location, because there's no correlation, right? If you not observe something, then you don't know about it. But we're lucky that GeoFluid community that your state is always related with some spatial scale. So with observation, you can constrain some vicinity. The error spectrum look like this, and I have included several more, a couple more lines to make it more interesting. So the truth signal is still looking like a large scale dominated red noise. Observation error is a white noise spectrum with a +1 spectral slope. The prior error is in red and the prior spread in red dash. After updating using the ensemble common filter, what you observed is error reduction in the spectral space. You have information coming in this spectrum, so you can almost think about this problem as individual wave numbers. So the Bayesian rule probably also apply in this wave number 1 here. Prior error variance is somewhere near 3, and the observation error variance is 0.06 something. And now you take the weighted average of the two, now your error gets reduced, and the spread gets reduced to somewhere 0.6. Because observation is very accurate at large scale, so you can make a lot of updates here. If you look at on the right-hand side, the small scale is quite different. Small scale observation is very noisy. It's individual sampling noises, sorry, not sampling noise, measurement noises on each sensor. So the variance is huge, while our signal, our vortex, is not having anything going on at the small scale. What data assimilation will do is it kind of raise the small scale noise if you don't have a large enough localization. If you update, you fit to the observation, and you kind of inherit some of this pattern of the observation. So this is also a problem of a single scale system, because now you update the whole thing with one specified parameter, how large the observation error is. And now this kind of error reduction or error growth is always not controlled by the user. However, if we decompose the scale into, decompose the state into spectral bands and perform the data assimilation separately for each band, you probably have more control. For example, the small scale error noise, you can choose not to assimilate it at all, because we don't have any small scale signal in our system. So that's something similar to super arbing, that we don't want to inject the error noises here in the small scale. So here, a final cell here, I introduced a tuning station. So you always wonder what's the best ensemble size, what's the best localization distance, and so in a certain configuration. So I here introduce one thing you can play with. The parameters tuple here, I include several values as a candidate for the localization value. Now I design an array. So these will be trialed individually. So you loop over these values and run this, the test over one cycle. With all the other variables fixed, for example, observation density I fixed to 4 and other things. And I also only changed the local cutoff here with this parameter P here. Times the observation interval, just normalizing the localization distance. So here I can run this. So you see it's testing the parameters, 1, 2, 3. Yeah, in the meantime, I can look at the question. Okay, can Msda be used for parameter estimation? How can you represent model parameters in the spectral space? That's a very, very good question. The most difficult part for parameter estimation is how to define its location. And yeah, you have when you have observation, you always know where it is located in space and time. But parameters you don't know. But you still can establish a relationship between the parameter and the observed variables, the observation. So in that sense, the parameter estimation is similar to a state estimation. I also had a similar problem when I designed the multiscale algorithm. When I have observation at small scale located in spatial point, I don't know how much I should use that to influence the large scale component. Like there's a scale gap in between this relationship, so it's surely not a linear relationship. So I think this question is still open-ended on my side, because I haven't fully addressed all the issues of this cross-scale update. So if you have some very high frequency observation, you want to use it to update one model parameter that controls the large scale dynamics. The relationship might not be robust enough for you to do that. So you might need to consider whether or not you want to do it. Yes, so I want to say that for the relationship between the parameters and the observation, you are certain that they are related and they are very robust. And let's try to run the parameter estimation. It's okay. But yeah, when you are uncertain about that relationship, especially in strong coupled data simulation, coupling parameters between different modules with different time and spatial scale, yeah, these are, I think, are active research topics, and I will not say anything more than that, other than I don't know. Yes, the results are also out. Maybe you are not expecting this, but this is a typical curve if you try different localization distance and plot the root mean square error against that. Because if you don't localize enough, a very small one here, the localization equals 1 grid point, you are not fully using all the observation. That kind of, it's almost like you have observation, but you localize and say that observation doesn't count and you throw it away. So that will give you large error. But also if you have too big localization distance, like 8 here, it means your ensemble size is small and the sampling noises will be included. So if we estimate the covariance between observed variable and the other state variable 8 grid points away from it, and I have only 20 ensemble members, and that correlation will have some uncertainty, some randomness. It should be, the true covariance should be almost 0, but actually I always get plus minus 0.3 or something. That will get included in the analysis. So it will get accumulated in the common gain so that the overall root mean square error gets increased. Mm-hmm. So here I basically say I need about 3 times the observation distance. So I can say, okay, I put 3 here. And I can go to tuning the other parameter, like let's say parameters equals, so for inflation, maybe 1, 2, 3.5. And I try to use a different observation error amplitude for my test here. Let's see what happens. I actually don't know what will happen because I haven't tried this yet. Okay, so yeah, the best observation error standard deviation is 1. And if you use anything outside of it, it's getting worse result, which is expected because the actual correct observation error standard deviation is 1. As we generate the observation, we perturb it by standard deviation of 1. If you, in the real case, if you have observation and you estimate its uncertainty and you don't know exactly how uncertain these observations are, and you make a guess. In your ensemble common filter simulation, you specify some value. This will demonstrate that if you deviate from the true value, you'll have some degrading the performance. Something else I want to try. Okay, let's go back to the scheme, the overall scheme. Here I will reduce the time steps to only 2 time steps. What I will try to do now is what I want to do. Try at low resolution again. And so previously I used localization distance equals 3 for an observation network that's 4 grid points apart, which give you the funky solution. So here and now I kind of know that the sweet spot is at 3 times the observation X interval. So here I put 12. It supposedly give you a better looking solution. Let's do that. Okay, so this is toggling because we only have 2 time steps, and we can use this to visualize what happens. Well, error does reduce from the prior, but you see that because we have a very coarse resolution observation, it's not reducing much. From a spectral point of view, when we don't have information, like this kind of observation, it's a thinned observation network. So you don't have this very large noise at the small scale. The issue for noisy small scale is gone. But at the same time, you only use part of the observation. Observation is so thin that you don't fully, you don't have a full power. So you only see a tiny bit of a large scale update in this case. So I think what I need to propose to do is we use the original observation density, but only update the large scale, if that's possible. Of course, let's try to use the full observation grid. So this is 1. Now to run 1 scale, but the scale is on large level. So the scales we have on the 3rd level of the pyramid. So it's a coarser resolution by twice. And we probably don't need the 12 here. We can use a shorter localization distance for that. We don't run alignment yet. Yes. Okay. Okay, it's finished running and the results. I'm not sure if the results is improved or not. Yeah, but you see now we don't have the small scale noisy problem. We use the full spectrum, but we have sort of a similar behavior of what I showed before with the thinned observation because you only update the component. What would be better is we use a smoothed observation instead of a thinned observation because I showed at the beginning that the thinned observation error variance looks like here and it is high level. So if you smooth it, it will drop down somewhere over here. It will be much nicer. Now the representation error is there's another problem with the representation error is the correlated error correlation in space. And I can demonstrate that by specifying a red observation noise, error noise. So I can do that by setting, so let's change this value back. 1 of 3. I think it's 12, and scales 1. Instead of a 1, we can set -1. Maybe still 3 and 1, yes. What will happen in this case? It'll be very interesting. You do see the cost of computation keeps growing if we have a larger localization distance. So I used 3 before, it kind of finished already, but now it's 12 grid points. So my Python implementation is kind of just using a lot of for loops. So this is not, there's no parallel computation anyhow in this. It's very slow. Should be completing in 2 minutes, if I remember correctly, last time I tried. In the meantime, I'm checking the chat for questions. Not yet. Okay, it's done. 2.5 minutes. Okay. Now the observation error looks like a more of a correlation going on in the spatial dimension. And if you make the, so here we're probably making the wrong assumption because the ensemble Kalman filter assimilates each observation point serially and individually. And when we assimilate one observation, we specify its error standard deviation, but we don't have a means to specify the correlation of this error with the other observation errors. The negative effect is that we fit to the observation too much. You see that the posterior error will take a shape. So sorry about the not consistent error bars, color bars. But the pattern of the observation error gets taken, inherited into the posterior solution, which is not always a good thing. So yeah, in this kind of pathological case, that the observation does have larger error. Now in this case, a white noise will have much lower large scale error variance here. And the red noise means you have less information on the large scale from the observation. So it's actually not updating. We can try again using a smaller error standard deviation and also reduce the resolution to increase the runtime. Before we do that, I want to point out one very problematic issue. If you can notice that before I talk about it, is the red dashed line here. So typically when we update in the ENKF, we expect that the posterior errors will kind of match the posterior ensemble spread because we Yeah, because we make the right assumption. But see how bad the ensemble spread becomes when we make the wrong assumption. We have the observation error is actually very large, but we made the assumption in our ENKF that is kind of small. So as a result, the posterior error is still large because what you have assimilated is actually this erroneous. But our ensemble spread gets reduced too much. It thinks we have corrected it a lot because we assume the error spectrum is a white noise. Now the ensemble spread is probably under dispersive in the next cycle. We have this problem carrying on to the next cycle that we need to keep somehow increasing this ensemble spread with inflation. In my 2020 paper, I addressed this, saying that we can try to chop this error spectrum into bands, and now in each band we are compensating for the for the mismatch of the assumed and actual error spectral variance. And if for the large scale we are way underestimating the observation error variance, we should perform some inflation in this band. I'm not sure if I will succeed in demonstrating that today because this code is so messy, but yeah, you get the idea. What we can try to do is for multiscale, let's see if I can do this. Let's set 2 scales, 3 and 1 in pyramid level. 3 and 1, so we both use the same localization. Using the same localization, we need to scale this by 4 times. So this is, remember, this is defined by the number of grid points. So in the large scale, number of grid points times dx is larger. So we inflate the large scale observation error by maybe 3 times, and we don't do anything for the small scale. So this is a multiscale loop outside of the ENKF. Fingers crossed. I don't know how it will work. So for this, it will process 2 scales. And the first scale is a large scale, so it updates super quickly because you have a smaller model grid. And the second, it will take 2.5 minutes to complete. Okay, let's see any Q&A. I believe I have addressed all the questions in the HackMD. I will go back and type my answers. So Laurent, don't worry, I will try to answer them offline. And if you have any suggestion on how to improve this efficiency, please also let me know. I hope in the tutorial next year, I will already include this example in the dapper, which is parallelized, and I think it will improve the performance by a lot. Also in the audience, if you're a dynamicist, please also, if you have any feedback on the design of this vortex model, if you have any idea on how to make it more chaotic or more of a small scale dominant, if you have some experience on that, also please let me know. Okay, we've done running. Now you see with this multiscale treatment, previously we fit the observation area a lot. Now it's more like towards the prior, more towards not updating at all. So it's also bad. But in this case, we are not overfitting the observation. Well, in fact, the observation is actually not too, yeah, we still slightly improve actually in the mid-range. Okay, so I'd consider this a partial success, but you see that when running the multi-scale system, you need to worry about scale. So these different scales. So yeah, if this tutorial module doesn't work out so nicely, that you can trust me because I already published a publication in this topic using even more rigorous testing. So what I tested here is only one realization. So I draw one random number and test it. In the paper I publish, I basically do this thousands of times and average all the output. So you should always keep in mind that when you run data assimilation experiment, people will comment on this constantly, that whether or not this is a case study, whether this will only apply for one instance and not be general. So the way we test a new scheme, new method, is that we run it in comparison with the old method in many realizations, drawing all kinds of random numbers and try to prove the point that this consistently better. The final, I have about 2 or 5 minutes, 2 or 3 minutes left. I think the final comment I want to make in terms of this multi-scale framework is that it doesn't necessarily beat the original ENKF, like echoing what's been discussed earlier. If you have in this tutorial module a very linear case, even if you run the multi-scale algorithm, it won't actually beat the common filter, which is bad as in a demonstration point of view. Yeah. Okay, I think I will leave it here. See if I have any more questions. If not, I can stop sharing my screen and we can have a coffee break. Stop sharing. And I hope you're all properly warmed up, at least in this morning and with my examples, because this spectral space is actually quite mind twisting. It does, I feel a little bit fuzzy after thinking about it for a while. So do we have more questions? If you have burning questions, you can raise your hand. If you think about more questions in the future, you can put it in the HackMD. I'll go to it. Other than that, if not right now, we can take the coffee break and we will restart in 11 o'clock. Is that right?
That's correct, yeah, thanks.
Yes, 11 o'clock. I will reconvene by then. I'll see you in a bit.
In a minute. I will first want to remind everybody that there's a debrief session Friday afternoon European time. And so you can play and turn around all the notebooks you've seen, Patrick's and Michael's. And then, then you can ask further questions on Friday. You have a second chance. Thanks, Michael. That was super useful and very well done.
Thank you.
Just say that Gare and Patrick and myself have been doing this for many times, but Michael's was his baptism of fire, so that was a bit more demanding.
Yes, thanks, yes. This is the first iteration, but yeah, keep tuned in if you're interested. I'll try to keep improving the module. Yeah. Thank you.
Thanks. See you after the coffee break with Julia.